13.8 billion years ago, everything we know, space, time, matter, didn't exist. Then, in an instant, it all began. Galaxies, stars, planets, life itself, born from the nothingness. How did this incredible event happen? What sparked the grand expansion that shaped our entire universe? Join us as we delve into the mysteries of the cosmos and unravel the origins of everything. Welcome to Unraveling the Origins. How did the universe begin? Let's explore the greatest question in science. The big question: was there a beginning? The universe's origin story is a quest that challenges our deepest understanding of reality. At the heart of this inquiry lies a paradox. How can something emerge from nothing? To grasp this, many scientists and philosophers have explored the nature of space and time themselves. Stephen Hawking, the renowned cosmologist, proposed that before the universe's birth, there was simply nothing, no space, no time. In his view, the beginning of the universe also marked the beginning of time. Asking what came before is akin to asking what's north of the North Pole, an irrelevant question within the framework of our universe. In this context, the universe's geometry, its shape and curvature, converges on a picture of a universe that curves inward, contracting and then expanding. Hawking's calculations suggested that the universe's very fabric, space-time, curves upon itself, looping back into a finite structure without a boundary. Searching for something beyond that boundary is as meaningless as searching for what's north of the North Pole. Yet others argue that perhaps the universe didn't have a definitive beginning at all. Instead, it might be part of a larger multiverse, an infinite ensemble of universes, each with its own set of physical laws and initial conditions. Some theories propose that our universe is just one bubble in an ever-expanding multiverse, constantly inflating, with regions constantly budding off into new universes. The bang that began it all. The most compelling explanation for the universe's rapid and early expansion is the theory of cosmic inflation. According to this model, a split second after the universe's birth, a brief but exponential burst of expansion, called inflation, occurred. During this tiny fraction of a second, the universe expanded faster than the speed of light, stretching space itself and smoothing out irregularities that might have existed at the moment of origin. Inflationary theory solves several cosmological puzzles, such as the horizon problem, how different regions of the universe exhibit nearly identical temperatures, and the flatness problem, why the universe appears geometrically flat. It suggests that our observable universe is just a small patch within a vastly larger, exponentially expanded cosmos. In fact, the universe's current size, about 93 billion light-years in diameter, is only a fraction of its total extent. Beyond our observational horizon, the universe may continue infinitely, with regions so distant that their light hasn't yet reached us. Some physicists propose that inflation isn't a one-time event, but an ongoing process that spawns an infinite multiverse of bubble universes, each with different physical constants and properties. Others suggest a cyclical universe, oscillating between periods of expansion and contraction, known as the Big Bounce. In this view, the universe didn't begin from nothing but has undergone endless cycles of rebirth. The geometry of the cosmos: flat, open, or closed. One of the key questions in cosmology concerns the shape of the universe. Is it curved like a sphere, saddle-shaped, or perfectly flat? Measurements of the cosmic microwave background, CMB, the faint afterglow of the Big Bang, indicate that the universe is remarkably flat. This flatness has profound implications. It suggests that the total density of matter and energy in the universe is finely tuned to prevent eventual collapse or eternal expansion. However, this precise balance raises a puzzle, called the flatness problem, akin to tossing a coin and having it land perfectly on its edge. How did the universe arrive at such a finely tuned state? Inflation explains this by stretching out any initial curvature, making the universe appear flat on large scales, regardless of its actual shape. The first moments, from singularity to quantum realm. The earliest moments of the universe, within the first trillionth of a second, are shrouded in mystery. At this point, the universe was unimaginably hot and dense, with temperatures reaching the Planck scale, or 10 to the 32nd Kelvin. Under such conditions, our current physical theories, general relativity and quantum mechanics, become incompatible. Gravity, described by Einstein's theory, warps space-time, while quantum mechanics governs the behavior of particles at tiny scales, where uncertainty and probability reign. In this realm, the universe was a bubbling quantum foam, filled with micro black holes and wormholes forming and annihilating spontaneously. The physics of this epoch, known as the Planck era, is an uncharted territory where our understanding breaks down. Physicists are seeking a theory of quantum gravity, an elusive framework that reconciles the two pillars of modern physics to describe this primordial chaos. Symmetry and its breaking, the birth of structure. Initially, the universe was perfectly symmetrical. The four fundamental forces, gravity, electromagnetic, strong nuclear, and weak nuclear, were unified into a single force. As the universe cooled, these forces separated through a process called symmetry breaking, leading to the distinct interactions we observe today. This symmetry breaking occurred in stages, beginning with the unification of the strong and electroweak forces, the combined force of electromagnetism and the weak nuclear force. As temperatures dropped, they split apart, giving rise to particles with mass via the Higgs mechanism. The Higgs field, associated with the Higgs boson, discovered in 2012, endowed particles with mass, shaping the universe's large-scale structure. The building blocks, from quarks to atoms. As the universe continued to cool within the first second, quarks, the fundamental constituents of protons and neutrons, began to combine into these particles. Meanwhile, electrons, the negatively charged leptons, joined protons to form hydrogen atoms roughly 380,000 years after the Big Bang, in an epoch called recombination. Before this, the universe was opaque, with photons constantly scattering off free electrons. The formation of neutral atoms transformed the universe from a hot, glowing plasma into a transparent cosmos, allowing light to travel freely. This decoupling of matter and radiation left behind the cosmic microwave background, a vital relic that provides a snapshot of the universe at that early stage. The cosmic dark ages and the dawn of light. After the universe became transparent, it entered the so-called Dark Ages, a period devoid of luminous sources. During this time, tiny density fluctuations, seeded during inflation, began to grow under gravity. Over hundreds of millions of years, these overdense regions collapsed into the first stars and galaxies, ending the Dark Ages and igniting the universe with light. The first stars, known as population 3 stars, were massive and short-lived, forging heavier elements through nuclear fusion. Their death in supernova explosions seeded the cosmos with elements necessary for planets and life. Over billions of years, galaxies assembled, clusters formed, and the universe blossomed into the complex tapestry we observe today. The mysterious dark components. Despite our progress, much remains concealed. About 27% of the universe's energy budget is dark matter, an invisible form of matter that exerts gravitational influence but does not emit or absorb light. Its presence is inferred from galaxy rotation curves and large-scale structure. Even more perplexing is dark energy, accounting for roughly 68%. It appears to drive the accelerated expansion of the universe, a discovery awarded the Nobel Prize in 2011. The nature of dark energy remains one of the greatest mysteries. Could it be a property of space itself, a new field, or a modification of gravity? The answer might reshape our understanding of fundamental physics. The future of the universe. What lies ahead? Based on current observations, the universe will continue expanding forever, growing colder and emptier. Galaxies will recede beyond our horizon, stars will exhaust their fuel, and cosmic structures will fade into darkness. Alternatively, some theories propose a big freeze, or heat death, where entropy maximizes and the universe reaches a state of maximum disorder. However, the true fate hinges on the nature of dark energy and whether the universe's expansion accelerates or slows. Ongoing and future missions, like the James Webb Space Telescope and gravitational wave observatories, aim to peel back the layers of cosmic history and answer these profound questions. Final reflections. The story of our universe's beginning is a cosmic detective mystery, woven with clues from the smallest particles to the largest structures. From the fiery chaos of the Planck era to the tranquil night sky, each discovery opens new questions. While the exact mechanism of the universe's birth remains elusive, what is certain is that our universe is a finely tuned, astonishing expanse, an intricate tapestry woven from the fabric of space-time, quantum fluctuations, and fundamental forces. As we stand at the frontier of knowledge, exploring the depths of space and time, we are reminded of our humble role in this vast universe. Our curiosity, ingenuity, and perseverance continue to push the boundaries of understanding, drawing us ever closer to unraveling the ultimate mystery, how everything began.